Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, and in this tutorial we are going to build our very first neural network, and we will see what happens when we stack all the primitives we've seen so far in a series of layers, and we will call this a neural network or a multi-layer neural network. So let's start. And here I am. Okay. So, in the previous tutorials, we've talked about perceptrons and fully connected and single neurons. And basically, this is what we can see in this illustration right here. And this is what we call a multi-layer neural network. This is what happens when we stack all these perceptrons in layers. And we can build and we can design it to be as wide as we want and as deeper as we want. And of course, we need to consider the computational resources we have. And let's see how we build this. So MLPs or multi-layer perceptrons is composed of one input layer and one or more hidden layers. And a final output layer, which will output what we want, our target. So it can be a regression task or a classification task. Now, every layer except the output layer option includes a biased neuron, which is fully connected to the next layer. So essentially, a biased neuron, we will see it. It's just a node with a constant value of 1, and it will have edges in the computational graphs, which will be learned. So the weights of this biased neuron will be learned. Now, when the number of hidden layers is larger than 2, we usually call this a deep neural network, but it's just a term, so don't take this as a rule. Now, MLPs are trained using Autodiff reverse mode, what we've seen in the previous tutorials, and basically we establish what we call the backpropagation algorithm, which is composed of two stages, the forward pass and the backward pass. And as you recall, both the forward pass and backward pass have similar complexities with the cost of additional memory complexity in comparison to Autodiff forward mode. Now, in the forward pass, for each training instance, the algorithm feeds it to the network and computes the output of each neuron, of each multiplication, and each consecutive layer. And then the output error, which is calculated as the final and output node of the computational graph, it's calculated, and then we are going to take the derivatives of the entire parameters with respect to this error. Now, basically, the idea is that the backpropagation algorithm, it calculates how much each neuron in the last hidden layer contributed to the output error, sorry. And this is basically establishing the chain rule, right? And we go from the end to the start. So, and the first layer is going to be the last in the backpropagation, in the backward pass. So, in short, and this is illustrated in this animation right here, for each training instance, which can be, of course, a batch of samples, the backpropagation algorithm first makes a prediction, which this is the forward pass. Then we measure the error with respect to some loss function. And then it goes in reverse to measure the error contribution from each connection. This is the backward pass. And finally, using some gradient descent algorithm, we've seen a couple of them, we update the weight or the parameters in the direction that reduces this error. So we go down the loss plane. So this is nicely illustrated right here. So you can see basically some like two layers, and you can see some example numbers. And basically, every neuron is fully connected to the following, to a neuron in the following layer, to every neuron in the following layer. This is why it is also called fully connected layer. And basically, the final node is our target or our prediction, and we measure the error, and then we go backwards to update these edges. These edges are going to be our weights, our parameters, as we've seen in the computational graph. So let's analyze this a bit deeper, right? So we have a network, a very simple neural network here. So we have an input layer and two hidden layers, and we have our output layer. So if we are, so maybe let's take a look at the board here. So basically, our inputs are x's, and we have the neurons in the hidden layers, the phis. And we have the biases. So bias is just a node with a constant value of 1, and it has edges, which are the weights. Now, basically, we can take a look at the dimensions here. So our parameters in the first layer, so we have W1 and B1. So W1 is of shape 2 by 4 because we have 2 inputs and 4 neurons in the consecutive layer. And similarly, the bias is just 1 by 4 because the bias is connected to each neuron in the consecutive layer. And every edge here performs a multiplication and summation, just like we've seen. So a single neuron just performs or computes a linear combination of the previous inputs. Now, additionally, as we'll see, phi is the neuron is also activated with some activation function. We'll see that in a minute. And an activation function can also be considered as another layer. So we don't see it right here because we usually just draw them as the same layer. But basically, we have the single neuron which computes the multiplication and summation, and then another layer which computes the activation over this over the result of this multiplication and summation, this linear combination. Okay, so in this example right here, this is what we saw on the board. So we can actually write this function down. And what is implemented here is a very simple but long mathematical function. And we start from the inside, so our neural network F, which takes inputs X and is initialized with weights W. So we start from the inside. So first we have our input X. It's multiplied by W1 and added with bias 1, right? Just like here. And then we apply some activation function, phi1. And then we move on to the next layer, which is W2 and B2, so this layer. And again, until we reach the end, and the final output is right here. So basically, this is our neural network, F. Now, the key change that made it to a perceptron, which, as you recall, was activated with a step function, or the heaviside function, right? And it's brought upon the era of deep learning. It's the proliferation of activation functions. So we have many of them. We have met some of them before. So we have met the sigmoid one, the hyperbolic tangent one, and the most simple one, ReLU. So let's cover a few of them. So logistic function, the sigmoid, outputs a value between 0 and 1. So it's nice when we want to model probabilities, right? Because probability is between 0 and 1. But usually we don't use this activation function in the middle of the network. We just use it on the output, so we don't use sigmoid inside the network anymore. Similarly, for the hyperbolic tangent function, so it outputs values between -1 and 1, and it's usually used on the output. So for example, when you want to model pixels, and pixels are between -1 and 1, so hyperbolic tangent is a good choice. But again, we don't use it as an activation function for the hidden layers. Now, I'll just note here that we'll see in the coming tutorials that we have something called recurrent neural networks. And in recurrent neural networks, and the sigmoid and hyperbolic tangent functions are heavily used inside these recurrent neural networks. And this is the only case where we still use these functions within or inside as is as activation functions. Now, we have the most simple one, the rectified linear unit, ReLU, which is it's a very simple one because it just performs the operation max between 0 and your input. And we actually can look what it looks like. So we can see here that everything that's is positive is passed on, and otherwise it's zeroed. Now we have a slight problem here at the point of 0, because this is not differentiable, but we usually define the derivative to be here to be 0, and we are good to go. So in terms of computation, this is the fastest one probably to calculate, and this is why when you design a neural network, you should probably start with ReLU and see what performance you get. And if you want to maybe squeeze a little bit more performance, you can try the newer ones. So still within the linear unit family, we have leaky ReLU, we have exponential linear unit ELU, and we also have the newer ones, which is GELU and SiLU. And if you take a look, so you can see that most of them behave quite the same, just the slope of the negative part is a little bit different. And you can usually use them to squeeze a bit more performance, but basically for most applications, ReLU still works pretty well, and it's faster to compute than the other ones, which include maybe calculations which are more expensive. Now, just for completeness, there's also a new activation function which is called Swish, and Swish is very similar to SiLU. Okay, so it behaves really similar. So if you see Swish, then it usually performs like SiLU. So just a note. Okay. Now that we have the building blocks, we have all what we've learned in the previous tutorials and what we've seen today with the activation functions. Let's design or implement a neural network. And the idea here is that we are going to code layers and not networks. We are going to take a modular approach, just like you build, for example, a castle from Lego, right? Then this is exactly what we're going to do. We are going to build large neural networks, but we have the basic building blocks which are going to be stacked together. And let's see what each building block has to implement. So how do we design a layer? So layer, as to specify, each layer needs to provide 3 functions. The first one is the layer output given its input. So basically zk plus 1 equals to the function that is implemented in the layer. So for example, it can be a linear layer which just performs the summation and multiplication we've seen so far for a single neuron, right? It can also be an activation function, so f can be ReLU for example. It's just a function, okay? The second one are the parts that we need for the backward pass, for the backpropagation, are the derivative. So we need to know the derivative with respect to the input. We need to know just the single step derivative. So the derivative of the input of the output with respect to the input, right? And we'll see everything in a minute. And the third functionality is the derivative with respect to the parameters, right? So we want eventually to update the parameters of the layer. So for an activation function like ReLU, we don't have any parameters. But for example, for a linear layer, we have the parameters of W and B, right? So they perform the fully connected multiplication and summation, this linear combination. And it's illustrated right here. So let's start with the left part, which is the forward pass. So we have our input, which is V1 or V0 usually. And then we have stack of layers. Each layer performs this operation according to its function. So it can be linear activation. It can also be an error calculation. So for example, we can have an MSE layer, which calculates the error of the input with respect to some target. Eventually, we get to calculation the error. After we calculated the error, we are going to use the other functionalities, which are the derivatives. So each layer needs to implement. These are the primitives we've talked about in the previous tutorial. So we need to know the derivative of the layer of the function that is implemented in the layer. So we need to know the derivative of multiplication, of summation, of ReLU, of sigmoid, and etc. Right? So we begin from the end. So we are going to call these deltas. So the deltas are what we backpropagate to the beginning, and basically this is an auxiliary variable that is going to help us calculate the gradients and the updates to the parameters. So we begin from the end, and we have the delta L plus 1, where L is the final layer, the lost layer usually, and it's going to be 1. So if you recall, where, for example, in PyTorch, the Autodiff reverse mode is called autograd in PyTorch. It's the derivative engine. So if you recall, we implemented it using loss.backward, and the input to backward was just torch.tensor 1.0. So basically we start from a scalar, and this is the scalar right here, 1, this one here, because the derivative of the error with respect to the error is always 1. So this is the one that starts our calculation. So AutoGrad, which is an engine for vector Jacobian multiplication, it only knows how to calculate gradients. It doesn't know how to calculate Jacobians, and it assumes that your gradient calculations start from a scalar. So this is the scalar right here, and it's usually 1.0. And then we go backwards until we reach the first layer, and each layer provides us with this functionality, which helps us to calculate the gradients. Now, if you recall, each time we do this, the first step, then since you are using Autodiff reverse mode, this activation, these outputs of the layer are saved in memory. And we are going to use this saved in memory, this cache, to calculate our gradients, as we'll see in a minute. So if we zoom in, we can see this functionality implemented of each layer. So each layer needs to know what it implements, what the function that is implemented. So ReLU, Sigmoid, linear, whatever. And each layer also has to supply us with, to provide us with the derivative with respect to the input and with respect to the parameters. And this is also illustrated right here, what happens inside the neuron, right? Okay, so let's cover it a bit deeper, right? So what is the backpropagation algorithm? And let's do it step by step, and then we'll see a proper example of it. So the idea is to implement the chain rule, right? Just like you've seen before. And basically the for-press just calculates the outputs of applying the function. The for-put is what we will also do during at inference time, right? And the backpropagation is it's what is done also during training, where you need to update your parameters. And the idea is that we are going to, from each layer, we are going to backpropagate something called this delta, which is illustrated right here. And these delta are defined as the derivative of the error with respect to the output of the layer, of the current layer you are at. So let's see it happens. So we are currently at layer number k, and we want to know that how to update the parameters of layer k, right? So we need to do a couple of things. The first thing is just to apply the chain rule. So basically we can write de to dzk as de dzk plus 1 to dzk plus 1 dzk. So basically what we did here is we will take the if you want, when you want to calculate the derivative of the error with respect to the input of the current layer, you just take the derivative with respect to the output of this layer. So this is the k plus 1, right? Just this one. And this is going to be called delta k plus 1 because we are going to get it from the following URL, from the consecutive layer. Remember, when we do the backpropagation, we start from the end. So the next layer provide us with this delta. And we now only need to know the derivative, the one-step derivative. We just need to know the derivative of the output of the current layer with respect to the input of the current layer. And this is something which is easy to implement. We don't need to perform a lot of calculations. We just need to know the one-step derivative. And basically, this is something which is given or implemented beforehand, right? So each function in PyTorch can be thought of as a primitive, which we know how to calculate the derivative. So we know what is the derivative of the sigmoid function, okay? And basically, this is going to be called delta k because this is what is going to go to layers dk minus 1, right? So this term is going to be called delta k, and we'll see it in a moment in a more ordered way. Now, we also need to calculate the gradients with respect to the parameter. We only care about the derivative with respect to the input because this is what is going to go to the previous layer in the backpropagation, right? We also need to know how to update the parameters of the current layer. So we, again, can do this chain rule trick and basically write the derivative of the error with respect to the parameters as the derivative of the error with respect to the output of the layer, and multiplied by the derivative of the output of the layer and the parameters of the current layer. And this is something which is given to us. We know how to calculate the derivative of sigmoid, for example, with respect to the parameter, if there are parameters. So for sigmoid, we don't have parameters, so it's 0. But for example, for the linear combination, we know how to calculate the derivative of the product and the input. So we'll see it in a minute. And again, it's just we can write it as a function of delta from the consecutive layer, which is given. So basically, we need to know the one-step derivative of the output of the layer and its parameters. So very simple. It's implemented. It's pre-implemented, and we can just use it. Now here we assume the single dimension. That's fine. Okay. So for multi-dimensional tensors, we have we need to do another extension, which we'll see in a minute. And this extension is just moving to define Jacobians and gradients. And basically, this is what we covered in the previous lesson. And the idea is that we are going to using a trick to calculate Jacobians, but we are not actually calculating Jacobians. We are actually calculating a vector Jacobians products. And basically, we calculate gradients and not Jacobians. Okay, so this is illustrated right here. So during the forward pass, we save the activation in our memory cache. And then when we do the backward pass, we are going to use these activations to calculate the gradients, because the gradient functions probably require us to know the output of the layers. And we will see an example of it in a minute. So you will meet a lot of primitives, a lot of layers, a lot of functions, and some functions have parameters, some functions don't have parameters. So for example, an activation function usually does not have parameters. So ReLU does not have parameters, but a linear layer has parameters. A convolutional layer, which is in the next lesson, has parameters. So basically, when we work with modular blocks, we don't need to think about it too much, as long as we know what is the derivative of the primitive we are using. Right? We just need to know the one-step derivative, and we are good, because the backpropagation algorithm is step by step. So let's do a proper example, right? For example, let's build a neural network to perform regression of housing prices. And basically, we are going to build a very, very simple neural network. And the idea is that we will take two features of some data set. And these two features are going to be the size of the house and the number of floors, for example, or the floor the house is, the apartment is. And the output is going to be just a single one, the price of the house, right? And this is a regression task. So the loss function is going to be MSE, mean squared error, right? And we're going to build a super simple neural network, what we've seen before. And I'll just note that usually we use much wider and deeper networks, okay? So don't take this simple example as a good default for neural networks. Okay, I'll show you an example later, and later in the course we'll see a lot more examples. But just for this tutorial where we build our first neural network, this is going to do. So, but when you design your own networks, keep in mind that you probably need more neurons, wider layers, and maybe deeper. Okay, so what we have here. So we have two inputs, two features. We have 4 neurons in the first hidden layers, 3 neurons in the second hidden layers, and 1 output. So let's do this step by step, and we start from the end. Okay, so we easily the format is quite easy, right? We just do this linear and linear combination multiplications, and calculate the output. Now for our activation, we are going to use ReLU, okay? So the very simple activation function, and we'll see how it works. So let's see what is the solution for this, and then we will implement it in code, so don't worry. So we start from the end, and the end is usually calculating the error, which outputs a single scalar. Remember that, because in AutoGrad we are assuming that the output is the final node in the computational graph is outputs a scalar. So the error is the MSE, so we have the prediction of the network, and the YI, which is the target. So the target price, the ground truth price from our data, right? And okay, so we have the calculation. We also have linear layers, which are the neurons, which implement a fully connected layer. So basically, the output of the neuron implements the linear function, which is just WT UIN plus B, where UIN is the input to the network, to the layer. right? We also have an activation layer, so the activation layer is element-wise. So ReLU, for example, it just performs the max between 0 and the output of the previous layer, of the linear layer, for example, right? And it works element-wise, so it's ReLU for each input of the vector. Okay, so it's dependent on the number of features, of course. So we just apply it on every feature separately. Okay, and so we also have an activation layer. So let's, now that so this network is pretty simple, right? We only have linear layers and ReLUs. So let's analyze this a bit deeper and understand how we implement every functionality we just discussed. Okay, so the forward layer, the forward pass we start from the linear layer, which is, I think, the most complicated here between all the primitives. And so the forward pass implements the linear combination. So it takes, so zk plus 1 is the linear combination of the w's and b. Of the current layer. So B and W are the parameters, right? So this layer has parameters which are learned. And let's calculate the derivatives. So we remember that each layer has to implement three things: the forward pass, this is what we've seen in the previous line, the derivative with respect to the input, and derivative with respect to the parameters. And these two are just single-step derivative. We don't need to know the derivative of the error or anything else. We just need to know the single-step derivative. So the derivative with respect of the output with respect to the input, so it's just the derivative of multiplication, right? So it's basically W. Now, I'll just know that we are slightly abusing the notations here, and I'll talk about it in a minute. So just keep in mind, these are matrices and vectors, and this is multi-dimension. And in this case, our delta, right? So if you recall, then from our previous calculation, so delta k is what is going to be passed on to the previous layer, so to layer k minus 1, right? So delta k is delta k plus 1. So delta k plus 1, we received it from the consecutive layer, from layer zk plus 1. And it's just going to be the multiplication of the delta k plus 1 with the single step derivative of the input, of the output with respect to the input. And so it's delta k plus 1 wk. Now, what you'll notice here is that we in this case, we only needed to know the current parameters, which is simple, but we also need to know the derivative with respect to the parameters, and for that, so we do the similar decomposition, and for that you can see that we also need to know the input of the layer. Now the input of the layer is something that we saved in our memory, right? Because zk is the output of the layer zk of layer k minus 1. And we needed this in the memory in order to calculate the derivative with respect to the w's, right? So this is why we need this memory for the backpropagation, okay? And so similarly, we calculate the derivative with respect to the w's and the bias, right? So it's everything is going to be dependent on delta k plus 1, which we received from the consecutive layer. Cool. Now, here's the important note I wanted to mention. So in the above, we abuse the dimensions, right? Because this is not the proper way of getting the derivative of a vector with respect to a matrix. So it's kind of hard to think about what is the derivative of a vector with respect to a matrix. And the proper way of doing this calculation uses the Kronecker product, right? And however, since we assume, and this is actually true for deep learning where the error is a scalar, since we are starting our calculation from a scalar, our loss value, the computation, we don't actually need to calculate this Kronecker product because the computation is simplified to a simple outer product, which is what we did like by a wave of a hand, right? But it's actually true when the output is scalar. You can read about this a bit more in these links, but just know that while intuitively we did this correct, there's actually a reason why we do this like this. Now, just a tip here, when you are calculating backpropagation by n for homework, for example, it is always good to perform the calculation parameter-wise. So instead of thinking in matrix vector products, just do this for each parameter separately in a single dimension. And this is just to avoid dimensionality issues and some headaches that can be caused from multiplying vector and matrices. Let's move on to the ReLU layer. So it's much simpler, right? Because the output is just the element-wise application of the max function. And this layer does not have any parameters. So this is why we only have the derivative of the input with respect to the of the output with respect to the input, and it is just the heaviside function. So the derivative of the ReLU is the heaviside function. And basically, to maintain the dimensions, we are going to put this on the diagonal of a matrix. So this is just to maintain the dimensions. So basically, what is going to be passed to the previous layer, this delta is just delta k plus 1 multiplied by this matrix here, which is the phi tag on the diagonal. Okay, so no parameters for the ReLU function. And finally, we have the error layer. So the error layer is going to return us a scalar, right? So this is also where we are going to start our backpropagation from. And basically, this error is just the output of the layer minus the ground truth value, our targets. And this is going to return us a scalar. Now, here is the point where the backpropagation starts. So the final delta, or the first one in the backpropagation calculation, is just going to be 1 because the derivative of the error with respect to itself is just 1. And this nice property means that we start our calculation, our gradient calculation, from a scalar. And this is what AutoGrad is implementing, right? So we start our calculations from a scalar, and this is what goes inside the backward function, right? And this actually helped us avoid calculating the full Jacobians, and this is how we implement it efficiently. Okay, and of course the derivative of the output with respect to the input is the derivative of the L2 function, right? Just the MSE. So what is going to be propagated to the previous layer is delta k, which is just this calculation here, because the final delta is 1. So let's see it in picture. So the forward pass is very simple, right? Just calculating all the activations, and keep in mind that each z here is going to be saved in memory because we are going to use it for the backward pass. And the backward pass, so we start from the end. So delta 6 here is 1. And then we move on. We are backpropagating these deltas to the layers, and each layer implements its own derivatives, and it needs to calculate the final values. It needs to know these deltas. So this is just how it goes, and it's very simple. And everything here is the outer product, and everything that we explained so far still holds. So this is nice in theory, but let's implement it in PyTorch. This is why we are here. Okay, so let's implement our first neural network. So I'll just reiterate a couple of PyTorch stuff. We've covered this before, but we will do this again so it sticks. So we are going to. There are a couple of ways to define neural networks. And you can choose whatever is more convenient for you. And we'll begin. I'll cover 2 of them. And of course, you can combine them and do whatever you want. Everything goes. So every neural network, right, every neural network inherits from the parent class nn.module. And this is super important, don't forget it, because this gives us the skeleton for our neural network is implemented in PyTorch. And every neural network, even the super large ones, inherit from this model. So it's just a common language. And when we inherit from the nn.model, we need to implement 2 functions, the init function and the forward. And in the init function, we just define our building blocks, our primitives, what layers we are going to use. So we're going to implement this super simple network we've seen above. So we have the first hidden layer, which takes us from the input to 4 neurons, right? We have the second one, which is 4 to 3, and we have the output one, which just outputs the output dim. which is going to be 1, okay, in our case. And the next thing we implement is the for function, which takes as input, the features, right? And then we define how the building blocks are applied, okay? So the first thing we do is take X, apply a fully connected number 1, and then we apply ReLU over it, right? And then again, the second layer, so fully connected over X and ReLU, until we reach the output layer. Very nice. This is the forward pass. This is all we need to implement, right? Now, this approach to building neural networks provides us with easier access to weights. So once you create an instance of house prices MLP, you can just, and so let's say model equals house prices MLP is an instance of house prices MLP. So if you want to access the parameters, the actual weights, you can just do model.fc1 and it will print your parameters and their values. So this method provides easy access to the weights. The second approach, which is more readable and maybe perhaps easier to code, it's going to have the same idea. So in the init function, we define our primitives, but we are already determining their order. So basically, we are already placing all the fully connecteds in a single block, in a single list. So our hidden part is going to be a sequential of primitives. So basically we are already determining the order of the building blocks. So we have the first layer, ReLU, the second layer, ReLU, and the output layer. And the forward pass is just going to come down to a single line, right? So basically we are just doing output layer over the hidden of X. And basically, this is much easier to code, and I think it's more readable. But if you want to access the weights later, so for example, if you want to access the first fully connected layer, then you have to access the list and then the first input. So it's less, I would say, it's harder to for example, if you want the third layer, then you need to search inside this list what is the number of the third fully connected, because you also can have activations, and you need to actually consider that when you number your layers. Okay. Now I'll just note this is a super simple layer, a simple network. So we have 4 neurons, 3 neurons. This is not what we usually do. Okay, usually we are doing this much deeper and much wider. So for example, here we used the hidden dimension of 256, which is so powers of 2 are usually what we do. So you can start with 128, 256, 512, 1024, and so on, right? Okay, so let's see how we can train this neural network. It's very simple. So we actually have seen the training loop before, but we'll do it again and again and again. So we load the Boston house prices dataset. So this is just a super simple dataset of of a couple of hundreds of house prices, and we have a couple of features. And you can see that we will need to scale these features. So this dataset is usually used in classic machine learning, right? And we are just going to use it as an example, but usually a classic machine learning algorithm will probably solve this as well. So we're going to take the first features. So remember, we are going to take 2 features and output the price, which is a single scalar. We separate the train and test. We perform scaling, just like we did before. And then we are creating a dataset, a tensor dataset. So here, up to here, it's still NumPy, right? And we need to change these NumPy's arrays to tensors. And we've seen a couple of ways to do this in the previous lesson, but we can actually have a class in PyTorch called tensor dataset, which will take the NumPy values and convert them to tensors, right? So we just print here that everything went smoothly, and this is after the scaling. So, and I'll just note the torch from NumPy is the older way to transform from NumPy to tensors, and today we are just doing torch.tensor over the xtrain. So we do this here just to show you that it still works, but in practice you should use the torch.tensor. Okay. Now we move on to define our hyperparameters, right? So what hyperparameters do we have? So when we create an instance of our process model, we need to tell it how many features are input. So we have 2. We need to tell it how many features are output, and we have 1 because the price. We also need to define the batch size. It's a hyperparameter, of course. We need to define the learning rate, the number of total epochs, and our criterion, right? So we use the MSE for regression. And super important, don't forget to define your device at the top of your code. So we want our code to be able to be run on machines with that have GPUs, CUDA 0, or don't have GPUs, so CPU. And next we move on to define our optimizer. So we'll use Adam, and to initialize optimizer, we need to give it the parameters of the model. So each class that inherits from nn.module has this .parameters field, and you can just use it to call your entire parameters of the model, no matter how many there are. And then we feed it the learning rate. Okay, and now we are moving on to our training loop. And to do this, we are now need to initialize the data loader. So data loader, what it does is going to separate our data to batches, and it's going to shuffle them. Okay, so this is why we need the data loader. So data loader takes in the data set and separate them to batches, and shuffling and helping us implement all this boilerplate code that we don't want to deal with. So our training loop, which looks more of the same usually. So the outer loop is the epoch loop, and the inner one is the iterations, the gradient updates, right? The first thing we do is we change the model mode from to train mode. So basically each class that inherits from nn.module has this field. So what this line is doing is telling some layers that they should be in training mode. So some layers, for example, dropout or batch normalization, we will talk about them in the following lessons. Basically, they behave differently at train time and at inference time. And in this simple network behavior, this line does nothing because we don't have layers that behave differently at inference and train time. So this line does nothing, but it's good. It's a good practice to put this before you start your gradient updates loop. So we then iterate over our data loader, our batches. We take our features and targets and move them to a device. It can be CPU or GPU. We do the forward pass, right? So basically when you call model and the input, it just calls model.forward. Now the reason we don't do this is because this type of forward pass is implementing more stuff, calling something called hooks and things like that. We don't go in this course, but you can read about it more in the PyTorch documentation. But basically, it calls model.forward and more. Okay, so just in the background, don't worry about it. Then we need to calculate our loss. So the loss is the final node in the computational graph, and it outputs a scalar. So we have the outputs, the predictions, and the targets, and this returns a scalar, the loss value. Now we move on to the backward path. So the backward path has 3 lines, which are always in the same order. So the first one is optimizer.zeroGrad. This function cleans the gradient from the previous iteration. Basically, it goes for every parameter and cleans or zeros its .grad field, right? You can also set this .grad to none. We'll talk about it later in the course to save some memory, because 0 is a number, so it occupies some memory. The next step, after we clean the gradients, we are calculating the gradients values, so loss.backward. So it's just like we did in the previous lesson, and this is calling to autograd, and basically it assigns the tensor.grad field. So basically, the parameters are going to be assigned values. And finally, optimizer.step, it actually applies the update. So it takes the values, and using the optimizer update rule, it changes the weights, right? So these 3 always come together. Now I'll just note that in some applications you want to accumulate the gradient. So for example, if you can't have a batch size which is larger than 1, for example, and you can actually accumulate the gradient values over batches by calling this line every couple of iterations. So if your batch size is 1 and every 3 iterations you call optimize at 0 grad, then when you calculate your loss, you're basically calculating over 3 samples, right? Because the gradient over 3 samples is accumulated. So just a more advanced application. So hopefully the loss will go down. This is what we want to see. And now we want to calculate the error, right? So when we calculate the error, we do two important stuff. First, we move on and we change the mode to model.eval. So in contrast to train, evaluation mode changes the behavior of several layers. In our case, it does nothing. But usually when you have dropout, batch normalization, and things like that, it's super important to call model.eval because the behavior of these layers change at inference time. Now, then we are going to wrap our accuracy calculation in this with torch.noGrad wrapper. And this is why we are doing this, because we don't want to track any operations over the parameters. So we don't care at this point about them, right? Because the reason we don't care is that we just care about the accuracy, about the forward pass and the error calculation. We don't want to update any parameters at this point. Okay, so this is our test run. Now we can actually see the computational graph, right? We can use TorchViz and we can print the graph and you can see the primitives. So basically you can see all the fully connected layers, right? And you can see the primitive, the edges of this computational graph, what primitive they implement. So for example, add MM, it's add multiplication. So this is just the linear combination derivative. We also have the derivative of ReLU, the consecutive layer. So basically we can see the everything in picture. And this is the computational graph, everything we talked about in the previous lesson. Very cool if you want to understand what happens in your network. Okay, we've built our first neural network. We are now going to cover a super critical concept in deep learning, which is Wights Initialization. And I'll show you why it's super important. We'll see a demo, and then we'll see how we can implement it in PyTorch. And I encourage you to try and play with different initializations to see what works best. In the end, we care about the final performance. And as you'll see, when we train when we train very big neural networks, usually their behavior can change vastly depending on the initialization. So a good initialization can lead to first convergence, and of course, some cases bad initialization can lead to divergence. But you also want to squeeze out the most performance you can, and it also depends on your initialization. So if you initialize in a good place, then at a good starting point, then you might reach a better local minima. So let's start with why we need to initialize weights, why not initialize them with 0, for example. So gradient descent algorithms, right, like we've seen before, AMS-Prop, Adam, these algorithm requires us to initialize the parameters to some values, and we use randomness to find a good enough set of weights. And we've already seen a couple of examples of randomness, right? So for example, we used the shuffling of the training dataset to prevent the network to memorize the order of the samples, for example, right? Now, training deep models is a sufficiently difficult task, and many algorithms are affected by the choice of the initialization. And now we ask, why not simply initialize with zeros, right? And so basically the idea is that since the training algorithm is deterministic, right? The update rule, everything is deterministic. Then if you initialize all the weights to the same value, then every weight will get the same update, meaning that the symmetry is not broken. And basically we are not able to learn different features because every update is the same for all weights in the layer, right? So the model will be stuck. Okay, so we won't be able to. You will see the learning curve. The learning curve doesn't move because each layer is all neurons in the same layer have the same value, have the same update. So we are not able to learn different features or different activations. So the idea is symmetry breaking. So initial parameters need to break the symmetry between different units. So we want each unit, each neuron, to learn some different trait of the input, some different feature, right? So if two units have the same activation function and they are connected to the same inputs, of course, then why would they have any different updates? So the algorithm is deterministic. The backpropagation is deterministic. There's nothing random about it. Now, note that usually you'll see that people constant the seed. So when you constant the seed, then the initialization, when you constant the seed, it means that even if you draw your initial weights from a random distribution, the numbers will be the same. So if you draw for the first neuron 0.13, then if you constant the seed, it will always be 0.13. But it doesn't mean that everything in the layer is 0.13 because it's still a random distribution. Basically, it affects the random number generator on your computer. So basically, if you want to train your network the same tomorrow, then you want to the same initialization that you did yesterday. So this is why sometimes it's good to constant the seed, just to get reproducible results. So I'll just note that there are a couple of papers that suggest non-random initialization. So what we'll see here is that we are usually drawing our weight from a random distribution, but sometimes it's better to have non-random initialization. And why? And the answer is very simple. Non-random initializations are much more simple, and it can help us easily reproduce results. So we can train big networks and have the same result each time without any randomness. So there are a couple of techniques to do this. So it's not exactly initializing with zero. There are two resources here. I really recommend taking a look, because maybe in the future we won't need to draw from random distributions, and we can just think of an initialization scheme which is deterministic, but it yields the same performance. So what kind of weight initializations we have? So anything you can think of, right? So uniform, normal, constant, 1, 0. Everything is implemented in PyTorch. But we can also do more smarter initializations, and as you've seen in the lecture, we can do Xavier and Kaiming. Both come in two flavors, the uniform and normal, and the difference is how you calculate the parameters of the distribution of the uniform or normal. So in normal, we are going to initialize with small values around zeros. And usually this STD is dependent on the size of the layers, right? So fan in and fan out are the number of neurons in the input and output layers. And basically these come from a deep theory. And basically we want to maintain, we don't want our loss to converge or to grow to very large numbers. And the idea is that we can do this smartly. So basically today the default initialization in PyTorch, you can see I just copied it from PyTorch. You can see that the default one is Kaiming uniform. But a lot of people initialize the networks themselves. So we'll see how we can do this. And basically what people usually use is some kind of a normal initialization. Okay. Now, of course, each initialization has its own hyperparameters. So, for example, here we have the gain, and we also have for Kaiming, we have the mode. So it's fan in or fan out, depending what you want to do. And the default this is the default for the linear layer. So for nn.linear, the default initialization is Kaiming uniform, and the gain is squared 5. And also the bias is initialized similarly. Okay, so before we do this in practice, let's see a demo. So here is a very simple network, much like we have seen in this tutorial. And what we are going to do, we are going to see how the initialization affects the learning. So when we initialize with 0, let's see what happens. So here's our training curve. You can see that nothing is learned. Basically, the curve doesn't move because the initialization is 0. So every weight learns the same thing, and basically we don't learn anything. So basically, we want to break symmetry. Now we can break the symmetry with random initialization. So let's see what happens when we initialize with when the weights are farther than 0, so very large numbers. So you can see that we have very big jumps, and maybe we get stuck because we are not able to break the symmetry very well, right? So we can see here the diffusion plane between the two classes. It's not that good. Let's see what happens when we initialize with values that are too close to 0. So basically, we will probably learn something, but it's going to take a lot of time. So it will take a lot of time to do the proper updates. And you can see that nothing is actually learned here. Again, very close to 0. And let's see what we use an appropriate training initialization scheme. So for example, Kaiming uniform, or Kaiming normal, or just normal with proper values. Then you can see that we get nice loss here, right? Nice last training curve. Nice dynamics, loss goes down, and the diffusion plane does its work, and everything works. So super important, right? So PyTorch, as every layer in PyTorch, has a default initialization. You can change it, okay? And now we are going to see how we can change it, but just keep that in mind. So when you initialize an n.linear, an n.conv, or every other layer, just keep in mind that PyTorch has already initialized them for you, but you can change it. Okay, so how we initialize weights in PyTorch? Very simple, right? So I'm going to show you, and we're going to use the same awesome prices MLP. We're just going to change the initialization, and there are two approaches here. I'll show you the one that I prefer, but you can take a look at the second one as well. So here is the idea. Here is our layer. Here is the network from before, the same one, but I added a method, and this method is called initWeights. And basically, we are going to call initWeights after we defined our building blocks. And what initWeights is doing is iterating over our primitives, our building blocks. So you can access that with self.modules very easily. Every network that inherits from nn.modules, you can access the modules via self.modules. And then you check what type of building block it is. So if it's nn.linear, let's change it to Xavier normal instead of Kaiming uniform, right? And you can do this for every kind of primitive. So you can add another elif here. So else if is instance m of nn.convolutional layer, then do some initialization for the convolutional layer, right? So basically, everything is going to look the same. The only thing we change here is this, okay? So the training loop is the same. You can see the dynamics are a bit changed, so we get different numbers, but the test MSC remains around the same value, so 15.34, and up there we got 15.39. So slightly different, but you can see the effect of a different initialization, and I encourage you to play with it. So initialization is also a kind of hyperparameter which you need to tune. And we are going to end this tutorial with a very interesting phenomenon, and something which is essentially changes what we know from classic machine learning. And it's going to be called double descent. And it's a very strong name, right? And basically, if you recall from the machine learning course or from our recap tutorial, we talked about the bias variance trade-off, and we also talked about underfitting and overfitting. And usually, what we saw is this going down and then going up. And when it went up, it was overfitting. When it was down, it was underfitting. And it happens when we are using the classic machine learning algorithm. So for example, SVM, logistic regression, and stuff like that. But in reality, what we see in deep neural networks is something very wild, which is called deep double descent. We are not saying it always. There are some cases it happens, but you can see it. So basically, the idea is that we start like you would expect, and then at some point you get the second descent. And in the second descent, you are actually escaping the overfitting and getting to better results than when you thought you were at the best port. Now, in order to alleviate this, usually we can use early stopping or regularization, but we still don't fully understand why it happens and how we can amend it. So let's dive a bit deeper. Now, what we see in this graph here is that as we increase the number of parameters, the complexity of the model, the test error initially decreases, and then just as the model is able to fit the train set, which is what we usually call the overfit part of the training curve, right? Actually, what happens is that we get a second descent. Now this is different than what we saw when we talked about the bias variance trade-off, right? Now double descent also occurs in other cases. I'll show you in a bit. Now we actually have names for that. So let's talk about model-wise double descent. So this is the first type. So in this regime, we see that the bigger models are worse, basically lead to overfitting, right? This test curve going up and training curve goes down, training error goes down. So basically, what we thought was the best spot to stop this plateau here, then actually it's not. So basically, what we can see here is so first let's give names to the regimes. So what you can see is that the peak in test error. So when you thought you are in super overfitting, right? So this is going to be called the interpolation threshold. This is the point where we are barely fitting the train set, basically memorizing the train set. So this point right here, when the training error is very close to 0, and the test error is very large. So what actually you can do is increase the complexity even more. So basically just add more parameters. So make the network deeper, wider, and basically you can actually escape this critical regime and actually get better performance, right? So when you thought that so what you thought was that I will increase my model complexity, I will make my network bigger. And what happened is that the test curve went up. So you said, okay, I'm overfitting, but actually what you needed to do is increase even more. So then you would escape this. We also have another regime where more samples are. So basically here we take a look about the model size. Now we can talk about the data. So basically for you can see here that increasing the number of samples. So we have 4K samples, and in this color, and in the green we have more samples, more data. So you can see that increasing the number of samples shift the curve downwards towards the lower test error, right? So basically, depending on the model size, of course, you can see that basically it might look like more data hertz, but it's not the case usually, and basically the model size is what you should be changing. Okay. And finally, we have something which is also relevant for us. Maybe we won't be able to create very big networks, but we can actually train for a longer time. So something called epoch-wise double descent. So basically, this is a regime where training longer reverses overfitting. So basically, you thought you trained a lot of time, and then the test error went up. So we said, okay, I'm overfitting. I need to do early stopping. I needed to stop the training a lot before. But actually, so if we'll take a look at the test error, and let's take a constant width parameter. So let's take 45, for example, and then we go up, and this is the number of epochs. So you started with a low training error, right? And then we start with a high training test error. Then you keep training, okay? And then the test error went up. This is the yellow area here. But actually, and then you said, okay, I needed to stop at something in between here. But what you actually needed to do was wait a bit longer. So, and then when you continue training, you actually get to even better results. So this is epoch-wise double descent. Now, in general, the peak of test error appears systematically when the models are just barely able to fit the training set. So just memorizing or get perfect score on the training set. Okay, so that's it for this tutorial. We have resources, we have links for more videos if you want to dive deeper. So thank you for watching, and that's it for today.